Good morning or good day to all of you. We plan and we decided to give a remedial lecture for the remedial exam that will be given tomorrow. So for today's lecture, we target to finish this in 30 minutes. Now, there are things to consider still on our quarter exam. There's a regrading of scores because there are items that are incorrectly provided as answers of Canvas. So scores may still change, but we set the perfect score at 110. And if the passing score is 60%, then it should be that you should get at least 66 points to be able to get the 60%. Now, the set score of 60% is part of our E-class record. So if it is 110 again, it will be 66 points at least that you should get. Now for tomorrow's test, it will only be a 10 points remedial test, and it will add on your score. We give everybody a fair chance to participate on that exam. However, we encourage especially those who have scores that are below or are equal to 66. Now, those who are high, have high scores, may decide not to take it. So we only encourage those who are 66 and below to take it. Now, to review or run through our exam, so generally this may be how our test items in the problem solving comes out. So for our remedial lecture now, so let's have the first item. So perhaps we have here an object that is suspended. So left object, the box that's the bigger box is our M sub 1, which is a 5 kilogram object, and this M sub 2 on the other side as our 2 kilogram object. Now we realize that when this is able to move, then the heavier mass or the bigger mass will eventually slide down while the other one will now move up. So acceleration will occur in two separate directions. Now we understand that if we are going to split these two objects together, we will see that in one object there's a tension, and that object will also have a weight. And by Newton's second law, if there are forces that will not be balanced, then it will result to what we call a net force. And a net force will eventually cause an acceleration to a given mass. So we have Newton's second law equals to F net, which is equals to mass times acceleration. Now, we see that the relationships of the forces in a body, which we call as a free body diagram. And if we take our free body diagram number 1, which if we look at free body diagram as the left object here, which is the 5 kilograms, then this is how the 5 kilograms would look like as a separate body. There's a force that pulls it up, and there's a weight that pulls it down. But the eventual motion of this body when you release the whole system is that this one will now go down because the other weight on the other side is only 2 kilograms. So the motion of this body will be downward. Now, if we base our net force to be mass times acceleration, then the mass that we will consider here is M1. M1 is our mass number 1, and having an acceleration that goes downward. Now, if A goes downward, then we usually indicate if it's a vector to be a negative value. So again, what are the forces that are involved here? Again, there's tension that goes up, and there's weight that goes downward equals to 49 newtons. And how did we get 49 newtons? 49 newtons is taken by multiplying the mass, which is 5 kilograms times 9.8 meters per second square. And that gives you your 49. Now, if tension goes up minus weight 1 that goes down, so we can have we could set up an equation that is T minus 49. And that T minus 49 is equals to mass times acceleration. Now, we indicate here a negative value because the acceleration is going down. No? So we have -5 for the mass, and then a, no, which is the acceleration a. No? Now, if we will transfer 49 on the other side, no, we will end up with what we call an equation number 1. No? And equation 1 will be, no, that t is equals to -5a plus 49. No? Okay, now we will relate this equation 1 with our free body diagram number 2. No? In our free body diagram number 2, if we look at the body on the right side, no, that body is the 2 kilogram body. No? Its weight, if you multiply it by 9.8, will be 19.6 newtons. No? Now, the tension on the cable is still going up, the weight is going down, but the difference of the two will be T that goes up minus W2 that goes down. No? So we will have this equation. No? Now, this T minus W2 represents the net force, which is equals to mass 2 times acceleration. No? Now, the acceleration on this side, no, for the 2 kilogram mass is going upward. No? So therefore, we will assign the direction of A to be positive since it's moving up. No? So that's why we have T minus 19.6, no, equals to 2A. No? So transforming and making it simply T, then T will be equals to 2A plus 19.6. No? Now we have a previous equation which we call as equation 1. So we will call this now as equation number 2. No? Now our equation 1, if that's T, no, and equation 2, since it is also equated to that same tension T, no, then we can probably say that they are equal. No? Now, being equal, then we can equate T, no, for equation 1 and then T for equation 2 to be equals to -5A plus 49, no, equals to 2A plus 19.6. And therefore, if you solve for A, now combining all the A values together and all the numbers together, now we will end up with an acceleration value of 4.2 meters per second square. No? So this whole system now will now move, no, with this acceleration. No? But the one on the left side, the body on the left side will go down, while the body on the right side, no, will now go up, no, with this acceleration value. Now for our tension, we could have, no, for our tension, if we'll calculate our tension, now we can use one of the two equations, no, either equation 1 or equation 2. But in this case, no, let's say we use equation 2. No? Equation 2 again being T equals to 2A plus 19.6. Now substituting the value of A, no, which is 4.2 times 2, which is the mass, plus 19.6. No? So the tension on either side, no, of our system will be equals to 28 newtons. No? Now we will see that 28 newtons will be greater for weight 2. Therefore, weight 2 will move up. No? But no, for weight 1, it's now lesser than weight 1. No? So weight 1 will now go down. No? Okay, so these are the two values A and T, now that we are now able to get for this answer. Now let's go to another example on the second law. No? Now, supposing we have a push cart now that weighs 100 newtons, no? And started from rests and accelerates uniformly until it reaches, no, a final velocity of 3 meters per second after moving for 10 seconds. And we are to determine, no, how much net force was present, no, to push that cart, no, that fast. No? So again, now basing on the second law, that F net is equals to M times A, no? We can calculate the value of M, no, if we have this weight of the cart, no, equals to 100 newtons. No? Now to solve the weight, or the mass I mean, we divide the weight by the acceleration due to gravity. So 100 newtons divided by 9.8 now gives us a mass now of the cart equals to 10.20 kilograms. Now, knowing the mass and knowing the value, no, of the acceleration, no, if we will try to find it, no, then we can get now the net force. No? Now, again, no, to calculate the acceleration, if the final velocity is 3 meters per second minus an initial velocity of 0 because it started from rest, dividing it by 10 gives us an acceleration of 0.3 meters per second square. So mass and acceleration are now available. So if we'll get the product of the two, we are now able to get a net force now that will cause this acceleration equals to 3.06 Newton. So we multiply mass times our acceleration. Now what is needed here is our knowledge on our idea of motion. Now another example here is to convert this value kilometers per hour into meters per second, and another value 30 feet and we try to find its equivalent length in kilometers. So what is 30,000 feet? 30,000 feet is roughly equals to a height that planes usually fly when it cruises at some altitude where there's less air friction. So it has to cruise at a height of 30,000 feet. Lower than that, it will spend more fuel because there's a lot of air friction that is present. So it has to reach something like 30,000 feet to be able to minimize its cost of using a lot of fuel. Now to convert 80 kilometers per hour, so we change that by multiplying it to 1,000 meters per kilometer. And then again, changing hours into seconds, we will now use this conversion 1 hour over 3,600 seconds. So what we see here is that we'll be able to cancel kilometers, and then hours will also cancel out, and that it will leave us now a value. So if we try to cancel out our units here, so if this is canceled out, and hours cancels out, that leaves us meter per second as our final value, equal to 22.22 meters per second. Now changing feet into meters, we have a conversion value of 1 meter, which is equals to 3.28 feet. So that's the conversion factor. So if we will now cancel out feet and feet together, and changing meters into kilometers, which is equal to 1,000 meter for a kilometer, then therefore we will end up with now a unit from 30,000 feet into kilometers, which will be around 9.15 kilometers. So that's how far in vertical distance is 30,000 feet. 9.2 kilometers. Okay, we will now move on to the next number. Now here's an item on components of forces, or component method probably. You'll use component method there. So if you are given the following vectors or forces, now our first goal here, if you are to find the resultant, is to be able to find the components of each value or each vector. And to be able to find the components of the vector, maybe these are the things that we need. We need to have the equation of the horizontal component equals to F cosine theta. So this is our equation. And for the vertical component, it is F sine theta. Now, how do we apply it, for example, for force number 1? So for F1, for example, the value of our horizontal component will be 47 newtons cosine 10 degrees. And that's how we get the first value of our component Fx, Fx1. Now for our component number 2, or our vertical component for our F1, that will be 47 sine of 10 degrees. We simply substitute directly the value of the angle. And we will get two values here, and they are both positive, 46.29 and 8.16. Now, we have to put them correctly, in each of these columns. Otherwise, we will get it incorrectly. So again, for fx or for cosine, it will be placed in the horizontal components. While for fy, or sine, it will be placed in the vertical component. Now, if we will do the same for f2, so 53 cosine of 45, it will give us 37.48. And then an equally the same value, we will also get the same answer for our vertical component. So 53 sine of 45 is equal to 37.48 also. Now, for our F3, we just found on quadrant 2, because the value there is 110 degrees. So you'll see that 61 newtons is moving towards the second quadrant. Now, its x component will be negative, at negative 20.86 if we will put 61 cosine of 110. You'll get a negative answer there. So we will include the negative sign here. So we will not disregard it. However, its vertical component, 61 sine of 110 will be 57.32. Now, adding these values together will now give us the total horizontal component and the total vertical component. So 62.91 is our total horizontal component, while 102.96 is our vertical component. Now, these two values, sum of our fx and fy, is important in finding our direction and in finding our resultant. Now, to find our resultant, we see that we are going to need our Pythagorean equation. So we will need our Pythagorean equation to find the resultant value. So we'll be squaring 62.91. And then 102.96 will be squared and added together. Now, their square root value will now give us the magnitude of the resultant at 120.66. Whereas our angle or direction can be determined by getting the arc tangent of theta. So if tangent theta is opposite over adjacent, which is fy over fx, then that will be the arctan, ang angle direction, which is arctan of 102.96 divided by 62.91. So that will give us an angle actually of 58.53 degrees. So this is now our direction. So if we combine these two values together, then we will now have our resultant force, which is equals to 120.66 newtons and moving at the direction of 58.57 degrees. So this is our final result. And we call this process again as our component method. Okay, moving further, so we go into our next item. So on rectilinear motion, so we have an electric car. Supposing it's traveling at an initial speed of 15 meters per second, and it's slowing down. It is decelerating, as they call it, until it comes to a stop after 5 seconds. So we are to determine the deceleration or the acceleration of the body, but we will see here that the acceleration will be negative because it is a slowing down process. And the distance that it travels for the time of 5 seconds. So to find our acceleration value, then we have the Vf value minus V sub I divided by T. And if we are to identify our given values, so 15 meters per second will be our V sub I. Our V sub F, since that's the time when it stops, so V sub F must be 0 with a time of 5 seconds. So if you substitute these values to our equation, then we will have 0 minus 15 divided by 5. So negative 15 divided by 5 gives us negative 3 meters per second square. So this is our first value. No? So the body will now slow down, no, with a uniform acceleration or deceleration of -3 meters per second square. No? Now, if you'll solve for the distance, no, so knowing the acceleration already to be -3 meters per second square, no, we could use an equation VIT, no, plus 1/2 AT square, no, where V sub I is not 0 here in this case, but 15 meters per second. Now, with a time of motion equals to 5 seconds. No? Now, our acceleration was given to be -3, so that's plus 1/2 of -3 times 5 seconds, no? And we square the time 5 seconds. No? So 15 times 5 gives us 75, no, meters. However, now 1/2 of -3 times 5 square gives us -37.5 meters. No? So the distance traveled for 5 seconds would then be, no, equals to 37.5 meters. Okay, so this is our next number, no, that now involves, no, our calculation for acceleration and our distance. Okay, so this is rectilinear or horizontal. Let's try a number, no, that is now using the free falling body. No? Now the item, no, the number is, or the example that we have here is a tennis ball, assuming it was thrown vertically upward. No? And when we throw something upward, we realize that it has to be thrown with an initial velocity. It's impossible to let this move, no, without an initial velocity. So it was thrown with an initial velocity of 6 meters per second. No? And definitely, if this is being thrown up, there's a point here where this one will reach, no, where it will no longer move. So we call that as the maximum height or the highest point. No? Now, what is that height? No? So the first question that we are to solve here is that we will determine the maximum height. No? So to get the maximum height, now then we have an equation S equals VF squared minus VI squared divided by 2G. And substituting our values, no, for a VF value, which is 0. Again, why 0? Because this is at the highest point. The body eventually stops moving when it reaches the highest point. So the final velocity at the top will be 0. But it started below with 6 meters per second. So that will be 0 squared minus 6 squared. And dividing the equation by 2 times 9.8. Now you see that 9.8 is indicated by a negative value because acceleration due to gravity is always going down. So since it's going down, so we always put a negative sign to that. So 6 squared will be 36 divided by 19.6. So that will give us a distance of around 1.84 meters. So this ball will not really go that high because it is not thrown with a very high speed. It's only 6 meters per second. So this one will go to as much as 1.84 meters. Now, how long will it take for that ball to go up? So VF minus VI over G gives us 0 minus 6 over negative 9.8. And the time for the ball to go up here will be a positive value of 0.61 seconds. Again, G is being indicated as negative because acceleration due to gravity is always pointing downward. So as a vector quantity, we can give it a negative sign. So this is both now our distance and the time for the ball to go up. Now, if we are going to determine the time for the ball to go up and reach the ground again, then maybe we can simply double 0.61 seconds. So that's the total time for the ball to be in the air. So if you throw the ball up and wait for it to go down, maybe the value there would be around 1.22 seconds. So that's simply double your 0.61 second time. Okay, so this is our free falling body.